Welcome to Extra Maths. My name's Lee and we are going to be finishing up our calculus sections. We've so far done 2 sessions on calculus and this is the 3rd and the last one. Now for me this is the most exciting session in that you actually get to see why calculus is such an important integral part of everyday life, and you can see what it has real applications, especially in the business world. So let's just quickly look at what we covered last time. We looked at sketching a cubic function, which we went through the 5 points we needed to know before we could actually do it. We then looked at some graph interpretation. We didn't finish this, so I'm going to start by doing a little bit more on that. Then we're going to move to maxima and minima problems, and these are where I say to you, it really is about real life applications and what can we actually use this in real life to do. And then, of course, rates of change. And, of course, you heard my story about Newton and Leibniz and how the two of them argued. And, of course, rates of change is what Newton was actually designing calculus for. He wanted to be able to use that in science. And you'll see some science applications, which in itself is exciting if you do not life science, physical science. So you will see the application very strongly to your physical science. Okay, so let's go across to the first one. Now it says the following characteristics apply to f of x equals ax squared plus bx plus c. Now I want you to look at that, and as soon as you look at that, let's take a color. You say to yourself, what kind of animal, or in this case, what kind of graph are we dealing with here? And as you can see, it's ax squared plus bx plus c, so this is a parabola. Now we've done enough parabolas to know how they more or less look. But now they're giving us all this information in a very different way. So let's take this up a little bit and have a look. Do you remember an earlier session where we learned that y equals f of x? And I talked about the fact that this would produce a coordinate x f of x. So in actual fact, what this is giving me is a coordinate. It's saying there is a coordinate where x was minus 1 and the y was minus 1, because the f of minus 1 is the y value. This is not a coordinate. We'll talk about that in a moment. This one here is also a coordinate. It says if x is 0, y is minus 4. And again, this notation is not coordinates. What did we say about f dashed? We said last time that f dashed x is actually the gradient, or the more glamorous word for it is the derivative. So what am I saying to you? I'm saying to you the gradient at x equals minus 1 is 0. Now from our curve sketching, what did we learn? We learned that if the gradient was 0, we in fact were talking about a stationary point, and in this case it would have been a local maximum, and in this case a local minimum. Why local? Because in actual fact this graph would carry on down here and there would be a much lower point than that, and likewise this graph would carry on up there, a much higher point than that. Okay, so basically what they're doing is they're telling me about a stationary point here. So let's have a look at what they mean by that. Let's take another color here just so it stands out. Right, so if we look at this here, what is it telling me? It's telling me if x equals minus 1, then the derivative or the gradient is 0. In other words, at minus 1, we have a stationary point. Now, of course, what do we know about a parabola? How many stationary points will a parabola have? Well, clearly, if you think about a parabola, it will either look like this or like this, but there's clearly only one stationary point. So either there or there. So we don't know yet which it is. I seem to be having a lot of fun today picking up things I shouldn't, so let's just go over here. Gradient is equal to 0. Right. So it's one of these two. And let's have a look at it. It goes on now and it says, the derivative is bigger than naught. That means the gradient is positive if x is smaller than minus 1, and the gradient is smaller than 0 or negative if x is greater than minus 1. Now, what I find extremely helpful here is to draw a kind of table. So what I do is I just knock out a little table here, and what I do is I say, okay, I know that at minus 1, the gradient would be 0. So that's the gradient or the derivative. And let's now look at what that means. So if I go over here, it says it's positive if x is less than minus 1. So I'm saying it's positive this side. And it's negative if x is greater than 1. Now, what does that mean? Positive means we're going uphill. 0 means we're turning. And negative, we're going downhill. So in actual fact, I've established that the parabola will look like that one and not that one. Okay, so let's draw ourselves a little sketch. Okay, we're going to input these points. We know that we have a point minus 1 over here. And it's best to write the coordinate on it. In fact, that was a very bad attempt at writing this coordinate, so let's just quickly erase it and just lift the screen a little bit higher so you can see it more clearly. Just keep it handy there. Right, so we have minus 1. My handwriting is definitely leaving a lot to be desired today, so let's try again. Minus 1. And we have a coordinate 0, negative 4. So negative 4 will be lower down here. Negative 4, so there it is. And we know that at x equals minus 1, we have a stationary point. Now, the good news is that means the axis of symmetry would have cut through minus 1. And we know this coordinate. They've told me that I'm going to climb till I get to there, and then I'm going to go down from there. And so there's the sketch of this parabola. Remember, too, to label your axes with a minimum required, which is your origin, the x and the y-axis, and the important points showing. So you can see it wasn't so bad to interpret this data. Now, why am I doing this with you? You'll say to yourself, well, you know, this isn't really necessary. We can do this completely a different way. Yes, we can. But if they give me a cubic, it gets that little bit more demanding. And if it's a bit more demanding, we need to have some methods in place, and this is what I was trying to do now. So let's go to the next example and let's look at it. Okay, it says graph. The following characteristics apply to the graph f of x equals ax squared plus bx plus cx plus d. So this is a what kind of graph? I'm sure you all remember from last time. It's a cubic. And remember, a cubic can look like this, like this, like this, or like that. This is determined by, between these two is how many stationary points we have. That tells us whether it looks like this or this, but let's have a look what we know. Now over here, they're saving on space. They're saying the f of minus 4, the f of minus 2, and the f of 1 equals 0. So in other words, we have a coordinate minus 4, 0, a coordinate minus 2, 0, and a coordinate 1, 0. So the fact that these are all x-intercepts, as you can see, because the y is 0 every time, means that those options are not going to be possible in this particular question. So we're definitely dealing with the left-hand side graph and not the right-hand side one. Now, if we look at this, what is it telling me? It's telling me we have stationary points at x equals minus 3 or at x equals 0. So there are two stationary points, again saying it either has this form or this form. Now, remember what I said to you. At this stage, the best thing to do is to draw yourself a kind of table. There are other ways to do it, but this table is pretty safe. We know this is the derivative, and we know that it's 0 at minus 3, and it's 0 at 0, because that's what that was telling me here. Good, so if I go over here now, it says the derivative is positive, so the gradient is positive, if x is smaller than minus 3. Smaller than minus 3 is this side, so it's going to be positive here. And it's also positive if x is greater than 0, so over there. This one over here, it says x, the derivative is less than 0 if x lies from there to there, so that's where it's negative. So in terms of my graph, positive means going uphill, naught means staying stationary, negatives going down, naught staying stationary, and positives going up. So that decides me that it actually isn't that option, but it's this top option. Okay, now you actually don't have to have put down those 4 different types right in the beginning to start, because you can see it comes out naturally if you use this little table method of getting a picture. Right, so let's go and see how this looks if we draw it properly. Let's get ourselves an axis. And let's put in some points. Let's stick to black. All right, let's start first of all putting in our x-intercept. So that's going to be -4. And then we have -2. And then we have 1. In fact, that's not really far enough over, so let's just space it a bit better. 1 over there. Okay, so that takes care of my x-intercepts. Then I know that at -3, I have a stationary point. Now this time, do you agree with me, they have not told me what the y value of the stationary point will be. So there's nothing I can do about that, but I do know it's going to happen on this dotted line. And the other one is that x equals 0, which is on the axis, so it's going to happen somewhere on that dotted line. What I do know is that it's going to climb upwards, obviously going through the first x-intercept to there, then go through the second x-intercept, go down to there, turn and come up. Now I can hear you saying, oh, but hang on a moment, I could have drawn this differently. And yes, you are quite right. You could have drawn this in many ways. I'll show you some other options that would be perfectly acceptable. But basically the examiner would be looking for, do you have the right shape? Are your stationary points at the right place? And do you have your x-intercepts? And if you have that, then it doesn't really matter exactly where you put that turning point or stationary point, because it depends. If they gave you that value, obviously it would matter, but if they don't, you can choose. So let's draw 2 other cases that would be perfectly acceptable. So let's take, say, a blue version. I could have done this. Made it really, really, really shallow. That would be fine. Or I could have even made it steeper. So let's try another color. But you see, the basic idea is, are we cutting through our x-intercepts? Yes. Are we turning at the right place? Yes. And is the shape more or less consistent? So any of those 3, and there are many, many more ways you could draw that. But it would give you the same idea, and your examiner would be happy because they would know you understood exactly how it works. So quite a simple, straightforward question, but if it's asked, sometimes can throw somebody if you haven't seen it before. But now you've seen it, so you'll be fine. Right, let's move on to the next question. Now, before we go on to the actual section, I just want to talk about something that is very, very useful. Often you'll get a graph interpretation question that involves you working from your original graph to the derivative and from the derivative back to the original graph. Now, as such, I haven't actually typed up any questions. I'm just going to put up some questions here for you and show you how we think it through. Once you get the hang of this, it's also a very nice question. So I'll start with the first option, which is where I say to you, given f of x, sketch, and let's make the sketch another color, f dashed x, just so you can see the difference. All right, so let's put an axis up there. And again, it can be absolutely any graph I feel like. So I'm going to put a basic one down first, and then we can go a little harder as we go along. Okay, let's go to black. Let's label it. It's x, and it's y. That's the origin. And let's put our original graph in peach like I had it originally. Let's imagine it looked like this. Okay, let's give this the coordinate -1, 7. Let's call this -5. Let's call this 1. Let's call this 6. And let's call this point over here 3, -4. Okay, and this is the graph of f. I want you to draw the derivative. Now, the derivative, first of all, we know that where there is a stationary point, we will have 0 for the derivative. So that means I already know that that's 0 at -1. And I know that here at 3, I will also have another 0 because that's where the gradient equals 0. Okay, so that's the first thing you'd always put in. Now, to get the rest of the graph, you would say to yourself, what is happening to this graph? Now, remember what I showed you with the little table. This is also very useful for this section. So what we would do is we'd say, okay, we're looking at f dashed x. We know that at -1 we got 0, and we know at 3 we got 0. What is this gradient here? Well, you can see it's going uphill, so it's positive. It's then going downhill, so it's negative. And then it's going uphill again, so it's positive. So that means these values would have to be a positive, negative, positive. And that would be the derivative of that function. Quite a nice little question. Not so bad. We're going to play around with it a little bit. So I'm going to try different versions of the graph. And you can see that even when I make it look as ugly as possible, it's not that hard to do. Right, let's have a look at another one. Let's put an axis up again. And this time let's make our original graph look a little bit more interesting. Let's do this to it. Okay, and let's call this -1. Again, I'm not doing too well on writing my -1s today. So it's -1, 5, and this is 2, 0. Please notice that it wasn't important where it cut the x-axis. I didn't even use that to draw the derivative. All I needed was the stationary points and what was happening with the gradient, because the derivative is the gradient. So let's have a look here. If we look over here, once again, if I'm going to draw the derivative, I know that over here we must get a 0 at -1, and here we'll get a 0 at 2. Now this gradient is going uphill, so that means it's positive. This is downhill, so it's underneath. And this is positive, so it's up, so there's your f dashed. Okay, you see I didn't even have to use that if I didn't want to, but if you find it easier to use that little table, please go ahead. So not a big deal. Let's try another one. Okay, let's put in a peach graph for you. Let's make it look a little different this time. This is 0, 7, and let's make this 2, 4. Okay, this is f. Right, so how did we work it? We started off, we said, where's the stationary point? The stationary point is there at 0, and another one at 2. This is going uphill, so it's positive. Then it's downhill, so it's negative. And then it's uphill, so it's positive. So there's the f dashed. Now, hopefully at this stage you're realizing that every time I've taken a cubic graph, I have got myself a parabola as the derivative. Now, does that make sense? Well, let's think about it. Do you agree with me? If my peach graph takes the form of y equals ax cubed plus bx squared plus cx plus d, then if I find the derivative of it, it must be 3ax squared plus 2bx plus c, which is clearly a parabola because it's a power 2. So in other words, whenever we find a derivative graph, it's 1 degree less, which makes sense. And so if the original was a cubic, your derivative will be a parabola. If your original was a parabola, your derivative would be a straight line. Now we're going to do some of those, so you're going to get a picture of that shortly. Right, let's go a little lower and stick another graph down and discuss one more of these before we move on to the other types. Okay, let's take this one. And let's call this -1, -10. Let's just tidy that up again. I've realized I'm definitely not good at writing negatives on this board. And this is 2, 0. Okay, so what do we know? We know that if we're doing the derivative, where there's a stationary point, we have a 0 and a 0. So at -1 and at 2. Now this time the gradient is going downhill. So we have a negative value. Now from here to here it's going uphill, so we're going to be above the axis. And then we're going downhill again, so we're going down. So yes, we could also learn, if it makes it easier for us, that if we have a positive cubic, remember I called it a slinky, then my parabola that results from the derivative will smile. On the other hand, if I have a kinky, which means I'm going down first and then long, then my derivative would be sad. Okay, makes sense? Negative sad, positive smiling, perfect. We're not going to get confused there. Right, let's take it now and look at another type of graph. Let's take a parabola. So let's supposing I've got a parabola looking like this. This coordinate is 2, -7. And I want you to draw the derivative. Okay, now what do we know? We know wherever there's a stationary point, which is here, this would now be a x-intercept. So at x equals 2. Then this one's going downhill. So if it's going downhill, it must be under the line. So let's go back to the little table for the first one we do, just so you can see it. We've only got one stationary point at 2. And we want to know what is happening to our derivative. Well, it's going down here, so it's negative. And then it goes up here, so it's positive. So that means it's gone underneath to there and then up again. And that's my derivative. Remember what I said to you? If it's a parabola, the derivative would be a straight line. So very simple, very straightforward. Let's do one more of these. And then let's try one other graph, and then we're going to go to the other type. All right, so let's stick in another parabola, and let's make it down here somewhere. Let's make this 3, -1, and let's call this f. Okay, so we know that at 3 we will have a 0. Now, what do we know about the gradient here? The gradient is going uphill, so we know it's going to be positive. And then the gradient's going downhill, so we know it's going to be negative. And again, you can see the derivative is a straight line. All right, so quite simple, quite straightforward. One more of these, and then we're going to swap to the other version. What happens if I give you the original a straight line? So let's stick it over there, and let's call this f. First of all, does this have a stationary point? Clearly no, a straight line doesn't turn. So you're not going to have an x-intercept for this derivative. However, do we know how the gradient's going? Yes, the gradient is always positive. So if that's so, let's have a look what would happen. Surely the derivative would have looked something like that. So you can see it's actually quite relatively easy to organize. Now see, I've been quite naughty leaving out your marking of your axes. Please don't forget to do that. I'm very naughty to have done that. Okay, so we've got a very clear idea of how to take the original to the derivative. Now, of course, if the teachers want to hot this up, and they do want to, they're going to rather give you the derivative and ask you to draw the original curve. Now, in actual fact, that is actually a little bit easier, I think. So let's see what you think. Let's have a look at another one. All right, so let's take a few graphs. And let's suppose I say to you, okay, I'm drawing the derivative, so I do want the blue pen. So let's say I've got the derivative looking like this, cutting at -1 and it's 3. And let's say I have one like this, just to give you a different version, 2. Now these are the derivative graphs. I want you to draw the original. So sketch F. Now remember what I said to you, the best thing to do is to organize a little grid. So let's do that. How many zeros are we getting? Sorry, I just took that up a little bit too high. Okay, we're getting a 0 at -1 and a 0 at 3. So that means our stationary points are going to happen there and there. Now, what do we know about the derivative here? Well, it's clearly negative. Over here, it is positive. And over here, it is negative. So what's happened? We've gone down, leveled out, gone up, leveled out, gone down. So this is very similar to that one I was doing earlier on, where I was taking the information and using it to sketch a graph. Now this is just giving you the information in graph form and asking you to sketch the graph. Not really a big leap. So let's have a look at this. So what I'm going to do, I know that my stationary point has to be somewhere there, and the other one has to be here. I know I'm going downhill till I get here, and then I'm going to go uphill till I get there, and then I'm going to go downhill again. So there's my F. So you can see clearly my stationary point's there. Now, sometimes in these questions, the teachers decide to ask you little questions without asking you to sketch. So one of the things they might have done before they asked you to draw the peach graph, so they might have said to you, find the x values of the stationary points. Classify whether they are maximum or minimum. Now that would have been easy enough if you're using this method, because you would have drawn this up, you would have known those are your two stationary points, and you can see that if this has gone from negative to positive, this is clearly a minimum, and this has gone from positive to negative, so it must be a maximum. And so you could classify it very clearly just using that technique. Right, let's look at this other one. Again, we're going to draw it. This time, how many stationary points have we got? Well, we've only got the 1, 2. So there it is, and we want to do the derivative. Right, so if we look at that, here, what do we know about the values? They are negative. What do we know about the values here? They are negative. So one stationary point, negative, negative, means go down, level out, go down. So it's one of these kinky kind of looking ones. So what do I know? I know that somewhere here, and I don't know exactly where, there's a stationary point. So I could have drawn this like that. I could have also drawn it underneath the axis. I could have drawn it up the top more, whatever I felt like, but the basic shape would have to be there where it's going negatively and then negatively again with a point of inflection over here. And that's really all you have to understand about this. So it's quite a relatively simple procedure, and I'm sure you can actually handle these more easily than the first lot in actual fact. So if they ever ask you this question, there's never a problem. Interestingly enough, the other day I saw a beautiful little question. What had been asked was you had to actually get the two graphs like this, and then the question asked you, so let's just go to black so I can put it in here. The question then asked you the following. It said, when is f of x times f dashed of x greater than 0? Now, if this is what you're looking at, it's not a problem, because you know from our graph section we did that if two things multiplied must be greater than 0, that means they must both be positive or they must both be negative. And in this case, there must be both of them. Of course, if it was less than 0, you would have one positive, one negative. But in simple terms, both positive, both negative means both above the x-axis or both below the x-axis. So all I would do is I'd take myself a vertical line along here, and I'd say, okay, if I look over here, what do I notice? Well, I notice that the peach one over here is positive and the blue one is definitely negative. So that won't be a solution. However, over here, peach is negative and the blue is negative. So I know from here to here, it will be true that it's greater than 0. So let's just take this line again. Let's check it. They're all negative, negative, negative till we get there. At that point, the blue one's above and the peach one's below. So it's not going to be there. So we keep moving until we get over here where the peach one goes above. So at this stage, I would say the peach one's above and the blue one's above till I get there. Right, picking up the line again and carrying on moving. We've got, there you can see the blue one's underneath and the peach one's above, so that's not going to work. But when I get here, the peach one's below and the blue one's below. So again, we can go here and we can say it would be this section here. So you can see it's actually quite a nice way to get to terms with that. So just remember that. It's well worth knowing this method. Just by the way, it was part of graphs really more than part of what we're doing here, but it's nice to know and to remember it. So you would give the solutions according to what you had on the graph. Obviously, this is not meant to be that question, but I just thought I'd mention it because it was a nice question I saw recently. Okay, now what are we doing next? We are going to move on to maxima and minima problems. Now, as you know, we've come across the word maxima and minima on several occasions in the sketching. You'll need to find that out in order to sketch. You might get asked to say whether something's a local max or a local min. And so this is just a natural extension of that theory. However, it will go beyond graphs. It will actually start going into real problems. This one here is still a graph question, a graph interpretation. And personally, if I was setting the paper, this question would be in it. Because for me, it's one of the best questions that they ask. Let's have a look at it. Okay, so we can see this says a function given by y equals ax squared plus b over x. Now let's start by looking at that. Is that a graph we recognize? No, clearly not. We can see the ax squared, which would make us think perhaps parabola, but the b over x would be problematic. We wouldn't make it a parabola anymore. So it's not something we know, so we don't really know much about it, but we certainly don't need to know what this actually looks like. So on the bright side, we have to only concentrate on what this is telling me. Now, what is it saying? It says the minimum value. Now, as soon as you hear the word minimum value, in your mind, you should be thinking minimum or maximum means derivative equals 0. So let's first of all start by calling this f of x equals ax squared plus b over x. And that means that f dashed at 2 would have equaled 0 in order for us to get a minimum. Now, you might say, well, why did you bother with this notation? Well, if I'm going to start talking about f dashed of x, and I haven't defined f of x, well, then there's no sense. Otherwise, what I could have done is I could have said to them, dy dx is 0, which is as good as that. But I quite like this notation because it's very specific. It tells you what the x is. Right, what else do we know? We know that at 2, the answer would have been 12. In other words, in that notation, the f of 2 equals 12. Okay, so that's quite useful if we know a coordinate on this graph, and we know the derivative is 0 at x equals 2. The question says, find a and b. So right, let's see how we're going to do that. Well, as I said to you, the first thing we know for sure is that the derivative equals 0. So we would take the derivative of f of x. But before we can do that, we have to flatten f of x. So f of x would be ax squared, and we can't have this b over x. So what we would do is we go plus b x to the minus 1. Right, so you can see now it is in a form that you can differentiate. So the derivative would equal 2ax minus b x to the minus 2. For those of you who've forgotten this lesson that we did the other day, let's just do a quick recap. Remember how it works. We go f dashed of x. The number there comes in front, so it's 2ax. We reduce this by 1, so it becomes, let's just write that a bit more clearly, it becomes 2 minus 1. This then becomes minus 1 times b, x to the minus 1 minus 1, which then, if you tidy up, is your 2ax, that's where you're getting that from, minus bx to the minus 2, which is the thing I produced there. But you'll find that once you've sort of worked on this section, you get comfortable with it, and it's not a big problem for you to sort out. Now, what do we know? We know that the derivative at 2 is 0. So what is f dashed at 2? Well, let's have a look at it. It's going to be 2a, we're going to replace the x with 2, minus b, and we're going to replace that x, which we could drop to the bottom like this, with 2. It just makes more sense to drop it to the bottom because now we can see it taking a normal form. So we know that that's 0, we know that this is 4a, and this is going to be minus b over 4. What can we do to make this look more user-friendly? Well, it's not too bad. We could times through by 4. So 0 times 4 is 0. 4 times 4 is 16a. And that will just be minus b. So in other words, b equals 16a. Now you've got an equation in two unknowns. So we're going to call this equation number 1. And we will know now we need to go and find equation number 2, because if you've got two unknowns, you must have two equations to work with in order to solve it. So there's your equation 1. So let's have a look how we're going to get equation 2. Now, what else did we know? We knew that we had the coordinate 2, 12. And again, I'm not doing too well on my 12s in my writing. So it's 2 and that's 12. And we know that f of x is equal to ax squared plus b over x. So the y value is 12 when x is 2. So we're going to go and plug it in, and we get that. Now obviously we have to make that look more user-friendly as well, just like we did with this one. So doing that, we've got 12 equals 4a plus b over 2. And again, who likes fractions? No one. So let's times through by 2. 2 times 12 is 24, equals 2 times 4 is 8a plus b. And if you wanted to, you could make b the subject again. So you could say b is equal to 24 minus 8a, equation 2. Now, I said to you, if you wanted to. So if you didn't want to, what would it have made a difference? It wouldn't have, because that would have been your equation number 2. And all you would have done is substituted equation 1 into that one. Now, the way I've done it, we've got equation 1 and equation 2, and they're both equal to b. So that means we're going to substitute 1 in 2. Doing that, I'm going to get 24 minus 8a equals 16a. Just to emphasize this is that part, and this is this part. Okay, so now we're going to tidy this up. So how are we going to solve it? We're going to say, let's get the a's to one side. So we have 24 equals 16a plus 8a. So 24 is equal to 24a, which means a is equal to 1. That's good. So we've got this one in the bag. Now, to find b won't be a problem if we go back to this equation over here, this one, b equals 16a, and we sub our a in. So let's substitute a equals 1 in that b equals 16a. In other words, b will equal 16 times 1, so b is equal to 16. So that takes care of that. You can see it's a lovely mark allocation, 7 marks. Something not too bad to do. It's a nice way to ask simultaneous equations, but why I particularly like this question and why this would be in an exam paper I set is it tests your understanding of minimum. Do you understand that the minimum is actually a coordinate on the graph where you could get the 2 for x and the 12 for y? And do you understand that the derivative equals 0 when x is 2? So for me, it's a lovely question. It's got that understanding, plus it tests your simultaneous equations at the same time. So yes, if I was the examiner, it would be there. It's a nice question to challenge you with. Right, so let's go on. So now we know that the equation is f of x equals a, which was 1, so it'll be 1x squared, plus b, which is 16 over x. Now the question tells me, so let's just highlight that maybe in yellow so it stands out a bit. Yes, there you go. The next question for 1 mark, so this is not going to require a lot of thinking, says give the equation of the vertical asymptote of the function. Now hopefully through all the functions you've been dragged through in your grade 11 and grade 10 years, you have realized that the vertical asymptote is when the denominator of a fractional, anything in a fractional form, is 0. Think of your hyperbola. Your hyperbola would be a over x minus p plus q. And you know that x equals p is your thing. So let's just write it out so you can understand. Oh gosh, I forgot to change the pen back to a normal pen. So let's go there. Y is equal to a over x minus p plus q. And you would know that that's there. X equals p gives me my vertical asymptote. And this would give me my horizontal on that. And so basically the denominator decides your vertical asymptote. So let's have a look at that. And in fact, you know where another nice place to mention this too would be on your trig function. And what the hang we write here, so let's talk about it. Do you agree with me if we look at y equals tan theta? That would be the same as saying y equals sine theta over cos theta. All right, and we know that that may not equal 0 because that would make the whole fraction undefined. So thinking of a cos graph would look like this. Do you agree with me it's 0 at 90 and 270? And of course you know from your tan graph that your asymptotes are at 90 and 270. So it's a nice tie into this whole thinking. But notice it was worth 1 mark. So all this explanation I've given you is certainly not required. But I just want to focus you in so you remember for future reference that if you are ever asked about a vertical asymptote, all you need to worry about is when will the denominator be 0. So let's have a look at what the equation actually was asking. So what's the only denominator I have to worry about? And you can see it quite clearly there, it's that x. So in that case, x may not equal 0. So the asymptote is x equals 0. So if we drew this graph, x equals 0, which is in fact the y-axis, would have been an asymptote for the graph. Okay, good for us. We don't have to draw it. We just had to say what it was. So answering this question, x is 0. Simple as that. And it's 1 mark, so we expect it to be as simple as that. Right, let's move on to another question. Now you can see this is where it starts getting exciting. It says a closed rectangular carton box has a square base. Now what I suggest you do when you read these questions, read them through firstly. Write the way through and then go back and highlight what is important. With a side x centimeters and a height of h, the total outer surface area of the box is 54 centimeters squared. Show that the volume is given by, and they give you an expression. Right, so actually if we look over here, we can see here that it says a square base. Okay, now that's quite important to know, as you'll see just now. With a side of x centimeters, so that's quite nice, we know what it is, and a height of h, so that's also useful. Okay, now as you can see it says the total surface area, now we're going to talk a little bit about that, is 54. So what I want you to imagine that this piece of paper I've got here is actually a box. Now what am I meaning by total surface area? What I mean is the area of the top, the area of the bottom, and the area of the 4 sides. Now I'm sure you remember in grade 11 you did a section on mensuration, which is your volumes, your surface areas, that sort of stuff. And you've been wondering where it's gone to. Well, it has gone nowhere. It is still very much here. You can find it in this section, your maximum minimum problems, and you can also come across it in your 3D trig, which we've already done. So you've had a look at that already, so you know what I'm talking about. So those are the sections that you can still come across this work, and I suppose you could even be asked a straightforward question with volumes and surface areas. But you'll find with examiners, what they're trying to do is they're trying to minimize the amount of questions they have to give you to test the syllabus comprehensively. So if they can put your mensuration, your volumes and surface areas in the calculus, why not? It just saves them a question. So let's have a look at this. Right, so you can see they've drawn a picture there for you. They've told you this is x, and that's h. And as I said, the total outer surface area is 54. Now, how do we get the surface area? As I said to you, it would involve the top. So let's highlight it so you can see what I'm on about. This top and this bottom. Now, do you agree with me that these would be x by x? So the area of that would be x squared and x squared. So I know my surface area will be 2 lots of x squared if I just take the top and the bottom of my box. Right, now let's worry about the sides. As you can see, there's one side, and you agree with me that this one side will have an area of x times h. Then there's a second side at the back here, which also has an area of xh, and then a one on the side here, which is also have an area of xh, and the one in the front, which I haven't counted in yet, which has area xh. So in other words, here I know that it's 4 lots of x times h. Now you can see what they're asking me to do here, to say this, the volume is given by this stuff here, is clearly not right. Okay, you can see that this is not going to work. Now, personally, I think this here is a v. So if you can just change that on your notes you're making. It's the volume that must equal that, not y. I think it was just a typing error. So let's have a look at this. So we have to find a way to make h disappear so we can get this expression. So let's go back to what else we were given. Okay, we were told that it's 54. So we know that 54 equals 2x squared plus 4xh. Now the only thing we don't want is the h. Excuse me. Right, so let's go over here and see how we're going to get it out of the picture. So we want to lose this, and to do that we are going to isolate it on its own. So what we're going to do is we're going to say 4xh plus 2x squared equals 54. All I've done is swing it around so that this is that side. Now that means that 4xh is equal to 54 minus 2x squared, which means h is equal to 54 minus 2x squared over 4x, because you're going to divide by this part to get the h on its own. Right, if we want to make that a bit tidier, we can go 54 over 4x minus 2x squared over 4x. And to tidy it up a little bit more, just so we can see more clearly what we're looking at, we can say h would equal, well, if I'm going to take this one, I'm going to say 2 will go into both of those, so it's going to be 27 over 2x. And over here, I'm going to get x over 2, because you can see that x will take one of those, 2 will go into there once and into there twice. Now, you can see some hope of us getting there if you look at that thing there. Now, volume. What do we know about volume? Well, the volume of any regular figure will be the area of the base times the perpendicular height. Now, in this case, it's a box, so the area of the base would be x squared times the height, which is h. So let's get the volume. So the volume is, let's just tidy this picture up a little bit because it's starting to look very colorful. Okay, if we look at it here, there's the base. So it's going to be x squared times my height, which is that here. Okay, but I know that height can be replaced with this. So that means my volume is x squared, and in place of h, I can go 27 over 2x minus x over 2. Now, if I multiply that in, I'm going to get 27x squared over 2x. And over here, I'm going to get minus x cubed over 2. Now, that's looking very promising because this x will take one of those out. So I've got 27x over 2 minus x cubed over 2, which is precisely that equation. All that I've done here is I've separated the numbers from the x's. And that's all right. And in fact, it's a good idea to do that. And they've told you to do it, so there must be a reason why. Right, so you agree with me that the first part of this question is just, in fact, a simple mensuration problem. I'm asking you to take the surface area and then to express the volume without an h in it. Very simple, very easy, something you've been doing since grade 10. Now, the next part of the question is where it comes to the calculus. It asks you to calculate the value of x for which the volume will be a maximum. Now, remember what I said to you. As soon as you see the word maximum, you think derivative equal to 0. So that's what we're going to do. We're going to go and work out what happens when the derivative is 0. So let's have a look at it. We know that the volume is equal to 27 over 2x minus a half x cubed. So the derivative would be, if I take the derivative of that, I'm going to get 27 over 2. Remember, that was 3, so that's going to be 3 times minus a half, which is minus 3 over 2, x squared. Now, to find our maximum, we need to put it equal to 0. So we're going to say, for a maximum, now, by the way, you know, this stuff is not essential, but, you know, if you're helping your marker and you're putting out your work, explaining what you're doing, it just makes it easier for them to follow your logic. And if they can follow your logic easily, if you make an arithmetic error, they can still give you method marks because they can see you knew exactly what to do. So my advice to you is, as much as possible, spell it out for your marker so they understand what you're doing. If you're suddenly now put it equal to 0, nothing said, they don't really understand that you knew what you were doing. Here they do. So for a max or a min, in fact, our derivative equals 0. So 0 is equal to 27 over 2 minus 3 over 2x squared. Now, we all hate a fraction. Well, not all. The maths teachers love them. But we know that if you want to get rich, you should open a bank that works in fractions because people don't like them generally. So you could cheat them very easily. Times through by 2. So 0 is equal to 27 minus 3x squared. And we can see now that we can get the 3x squared on this side equals 27, which means x squared is equal to 9, which means x is going to be plus or minus 3. Now, clearly, what was x? X was the length of the base. Now, if the length of the base is there, can it be a negative? Clearly not. So obviously, the negative option is not an option. So the answer would be x equals 3. Now, the question you might ask me at this stage is, okay, that's wonderful, Lee, but look at this. It says for a min or a max. So who's to say this is a maximum, not a minimum? Now, this is where we have some very interesting theory that can help us out. If it's a figure that we don't really know much about, we could find the second derivative. Now, if we do that, that's a constant, it'll fall away. This will become 2 times that, so it'll just be minus 3x. Now, what we need to know with this theory is that if the second derivative is less than 0, we have a maximum. And if the second derivative is greater than 0, we have a minimum. Now, we know the value was x equals 3. So if I go up here, v double dashed is equal to minus 3 times 3, which is minus 9, which is clearly less than 0, and therefore we have a maximum. So the answer to this is if our base was 3, we would have a maximum volume. I could have also asked you what is the maximum volume. Now that wouldn't have been a problem, because all you would have done then is you would have substituted this x value back into your formula for volume, and you would have solved. So let's just, for the sake of the question, go and do just that. Let's take it up again. We know the answer was 3. We know that the volume equation was 27 over 2 times x minus a half times x cubed. So if it is 3, it's going to be 27 times 3 over 2 minus a half of 3 cubed. And you can see you're going to get 81 over 2 minus 27 over 2. And if you do that subtraction, you can of course use your calculators, but let's be good and work it out. We're going to get, I think, 54. Let me just check I'm not lying to you. Yes, that's perfect, over 2. Okay, so the maximum volume would be that cubic centimeters, because they did tell me the unit. But that was not the question. The question was just what x value maximizes the volume. So really, that's a nice idea of how this is used. I'm going to do one more of these to do with mensuration, just so you can see it in action. So let's look at another question. Right, this one's a little bit more intricate in that the drawing gets a little hectic. It says a cylinder of radius r and a height of h, let's highlight that, is inserted into a sphere of radius 5. Now a sphere is just a ball. Obviously I can't represent it beautifully here, but it would mean that from the center of this ball to any point here, the radius was 5. So let's go and pop a center in over here. And do you agree with me if I drew it up to there or to here or to anywhere on the circle circumference, I would get a length of 5. So I'm going to draw it in here and call it 5. What did they tell me other than that? They told me the radius of the cylinder is r. Okay, and the height of the cylinder is h. In other words, from the top down here, all together is h. All right, so now it says determine an expression for r squared in terms of h. Well, if the total height of the cylinder is h, do you agree with me that this would be h over 2 and this would be h over 2, because that center of the sphere would be the same either end. It would be nice and symmetrical. So in actual fact, to find an expression in terms of h won't be that hard, because we know this would be a right angle. In other words, if I look at that, I could say to myself, well, that means that from Pythagoras' theorem, 5 squared will equal h over 2 squared plus r squared. The hypotenuse squared equals the two sides containing the right angle squared and added together. There it is. That's Pythag. Also, a good idea is to just let them know why you're suddenly stating that statement. Now, we're not finished because it said find an expression for r squared in terms of h. So at this stage, I can say 5 squared is 25. This is h squared over 4 plus r squared. And so therefore, I could say r squared is equal to 25 minus h squared over 4. I've now answered the question properly. Now it says, find an expression for the volume of the cylinder. All right, so how are we going to find the volume of a cylinder? Remember what I said to you, any regular shape, the volume is always the area of the base times the height. Now the area of the base of a cylinder is a circle. Think of a Coke can or whatever like that sort of shape, a glass. That bottom thing is a circle. So what we're going to do is we're going to find the area of a circle, which is going to be pi r squared, times the height. Okay, So now they want an expression for the volume. So now we have an expression that we can change it all to h, because we know that r squared is equal to 25 minus h squared over 4. So at this stage, I could say it's equal to pi r squared. Oh, sorry, let's just reverse that. Let's write it as pi h r squared. And then we can go over here and say pi h. And in place of r squared, I can put that in. So let's put it in another color so we realize it's a substitution. So it's 25 minus h squared over 4. They didn't say to me in terms of h. So if you'd left it up the top, they would have had to accept it, okay? But I think it's 2 marks, so let's just take it a bit further. We probably will need to do it at some stage. So now we times this in, so we're going to get 25 pi h minus, and if we times that in there, we're going to get pi over 4 h cubed. That would be their volume in terms of h. Not that they mentioned that, but it's, you know, we can do it just to show you how it's done. Right, let's go on down here. It says determine the height of the cylinder in order for its volume to be a maximum volume. Okay, so we've got the volume in terms of h. So let's work in h. It was a good idea that we did what we did. So let me just keep that there so we've got the equation handy. So the volume is equal to 25 pi h minus pi over 4h cubed. Now, maximum. For a max or a min, we must take the derivative equal to naught. So let's get the derivative. The derivative would be, now what type of animal is pi? Well, pi is actually a number. It's an irrational number, but it is a number. So the good news is we can go straight forward. So we can say the derivative of that will become 25 pi. And the derivative of this is 3 times that. So it's 3 pi over 4 h squared, because you reduce by 1. We're now going to put it equal to 0. And we're going to solve for h, because that was the actual question. Now again, we don't like fractions, so let's avoid working with them as much as possible. Let's times through by 4. So if we do that, we're going to get 0 is equal to 4 times that is 100 pi. And that's going to be minus 3 pi h squared. Right, so at this stage, we have 3 pi h squared equals 100 pi. And that means that h squared is equal to 100 pi over 3 pi. And we can see that that pi divides into that pi. So we've got h squared equals 100 over 3. And let's bring it up here. So that means that h is plus or minus the square root of 100 over 3. Now, the good news is, you know, height won't be negative. So we know we're dealing with a positive h. So h is equal to the root of 100 over 3. Now, it depends what the question said, but normally these questions, they would say to you, give the answers to 1 decimal place or 2 decimal places. So at this stage, we're going to pull up the calculator, work that out. If nothing was said, we would have just left it in its third form. We could have maybe made it a little bit better. We could have written it as 10 over root 3 if you felt like it. But it's not going to make it look all that much better. So let's go to the calculator and show the calculator in action. Right, here we have it. We want to find the root of, so we put that in, we put our fraction button in, we put in the 100, and we spacebar down to 3, and we press our equals. And there you can see it's giving it to me as a third, but we want it as a decimal, so I hit the button S to D, and I find that H is, and I better just bring it up for 2 seconds, 5,77 if we're going to give it to 2 decimal places. Okay, and I think it was in centimeters. Let me just check if that was the right unit. I actually don't know if we gave you a unit. No, it just said 5, so we don't know what the unit was, so we wouldn't say centimeters. We would just say units. If they had said to 1 decimal place, you would have answered H is 5,8 units. Now, a very nice question to do with this is to think about a Coke can and think to yourself, if you were manufacturing one of those, how would you want to get it to work? Well, you'd want it to contain a certain volume, which you would know. I think it's 330 at the moment. It used to be 340 mLs in a tin, but I think it's 330 now. Anyhow, whatever the volume might be, And you would want it to be streamlined, you want it to look attractive, but you would also know that to do the top section and the bottom section would be more expensive than doing the sides of the can. So a nice exercise is to work out, say that the top and the bottom of the can cost twice as much to produce as the aluminium around the actual can, and see what sort of proportions will come out, and you'll be amazed that in actual fact the proportions of the Coke tin that you see every day is pretty much right with that kind of thinking. So give that a try and you'll see for yourself. Okay, right, let's move now across to the next bit of work. The next bit of work we're going to work with is called rates of change, as you saw from my summary right in the beginning. Now, rates of change is basically just gradient. Remember what I said to you about old Newton and what he was up to? He was very interested in rates of change. And in fact, for the science people, I'm just going to give you an absolute thrill now for 5 seconds, because you're going to see science and maths come together, which is always awesome to see. So you must remember, you've learned in science, S is equal to UT plus a half AT squared. These are known as your equations of motion. And I'm sure you all have good memories of them if you do science. If you don't do science, don't worry about this. This is not going to affect you in any way. It's just a nice tie-in for those who do science. And then you get your acceleration. Now, these are known as equations of motion. Now, what I want you to see, or what I want you to think about, is, do you remember when they gave you this thing? Say they gave you some kind of drawing here, and they asked you for the velocity. What you did is you worked on the change in displacement over the change in time. And of course, the change in displacement over the change in time was your velocity. Now, velocity, remember I told you about this delta sign, it is actually d for delta, so it's ds dt. So in other words, it's the derivative. Okay, so let's talk about it. Let's see if this is true, what I'm telling you. Let's go here and let's take this equation S. We know that S is UT plus a half AT squared. And we know that if we want the derivative of that using t as the variable, u would be the only thing left because that's t to the 1. And 2 times a half is 1 AT. And of course, if you look at that, that is your formula for velocity. Isn't that exciting? I just get so excited when I see these kind of connections. Right, now if I want acceleration, same thing would have happened in science. I would have drawn velocity against time, and I would have looked at the change in velocity over the change in time. So, sorry, I've gone a little bit too high again. The velocity's derivative, if u is a constant, would just fall away, and you would just get a. And so that's a complete tie-in to how the science people were thinking. So I want to just put one thing out, and this is now for everybody, not only the people who do science, because this part you do have to know, but I want to console you with the fact that it's really very easy to use calculus in science. And even if you have never done science in your life before, I'm going to teach you some strategies that will make it easy for you. So what I want you actually to know, that is not important for you to know at this stage. What I do want you to know is the rate of change is basically the gradient. If it's the gradient, it is also the derivative, because remember that's the proper name, or the name we use in calculus for the gradient. All right, so it's the gradient. And in terms of science, and this we do need to know as maths people, if we're starting with displacement, now I'm going to talk a little bit about this in a moment. To get to velocity, I take the derivative of displacement. And to get to acceleration, I take the derivative of velocity. So that we do need to know, no matter whether we do science or not. This is going to be part of what we do. I just want to talk about what the difference is between this velocity and our distance as we've always known it. So let's talk. Right, if we're talking about displacement, if I'm starting over here and I'm going off on a little round trip and I end up back here, my displacement is 0, because displacement means from where I left to where I am as the crow flies. So distance would have been this whole scenic route I would have taken, but the displacement would be 0. So if I do the thing again and I go off on my little scenic route and I stop over here, my displacement would be this distance, not the scenic route. So that's the only difference between distance and displacement, nothing to get too worried about. Velocity is your speed, except it has direction. And this comes up when we throw things in the air and they come back. You'll see that the velocity shows negative, and it just talks about direction, whether it's going up or going down, depending on how we defined it. And yeah, basically acceleration, when we work with it, has got to do with gravity, the gravitational pull. But don't get too worried about any of that. The important thing to know is just this little drawing. And one more thing I want to add before we actually go across and look at the kinds of problems we get is that t is 0 at the start or the initial sighting. So initial or start always implies t is 0. So we're going to work with that in a moment in the problems, and you'll see it. Now, we're not only going to do science problems, we're going to do some biology problems as well, or life science and physical science problems. So you will see for yourself what I'm talking about. Right, let's go over here. It starts here, and this has actually got to do with money. So those of you that are going to do BComs one day are going to use calculus in your BCom to maximize and minimize real problems. It is estimated that the circulation of a magazine can be represented by the equation that. So let's just highlight our equation. Okay, I see it scrolled a bit here. There's part of the equation. So what I'm going to do is I'm just going to write in the 4,000 over here, because it's quite off-putting if it's over there. So there's your equation of your distribution or circulation of the magazine, where T is the number of years of publication. Now, we need to know that because when we're answering the questions, we need to know so many years, or is it months, or is it days, what is it? Okay. Now it says, how many magazines were sold at the time of the initial publication? And what did I say to you about the word initial? What do I mean? Well, as I said to you, initial, we're always going to say T is 0. So what we're going to do is we're going to take this equation, because this is the distribution or the circulation equation, and at the time of it first being sold, so T equals 0, the very first print of this magazine would be when T is 0, so 0 years. So we would literally go along and we'd replace every T with a 0. Now, of course, you don't have to show these steps because you know what happens if T is 0. The answer would just be the 4,000. So the circulation of 4,000 magazines initially. Okay, so that's straightforward enough. Now it says, derive an equation for the rate at which the circulation will change in T years. So what did I say to you? As soon as you see that word rate, so let's highlight it so we're stressing it, rate. We are talking about the derivative. So what we're going to do now is we're going to say, let's find the derivative equation. Now, if we take in the derivative of this, it will be 150 T squared minus 300. The T would fall away, and that's a number, so it will fall away completely, and that's the rate of change. Now, this will tell me how my magazine circulation is improving or not improving, depending how we're looking at it. Now it says, at what rate will the circulation be changing in 3 years' time? So again, the word rate is used, so we're using this equation. And they want to know it's 3 years' time. So we're going to say, right, the derivative at 3 is 150 times 3 squared minus 300. And we can pull our calculator up, and we can literally input this. So it's 150, 3 squared minus 300. And we can see it's 1,050 is the actual rate of change. Okay, so that's a nice, easy question. Now it says, determine the average rate of change. Now, as soon as you see the word average, all warning bells should go on, because average is not derivative. The rate of change is derivative. The average rate of change is the good old average gradient, which we know how to do. We're actually going to work out our coordinates of the 2 points that we're interested in. And then we're going to go and say, okay, fine, let's work it out. So let's go over here. They want to know T equals 1 and T equals 2. Let's just grab the equation and bring it down because it's a bit too high for me to use there. So yeah, so it's 50T cubed Let's just bring it down. Okay, it's forgot to change the pen, sorry. 50 t cubed, and I know there was a t squared, and I know there was a 4,000. Let me just go back and get that equation completely. 50t cubed minus 300t, and it's not t squared, it's just t, plus 4,000. So that was the equation we had, and let's call it something. So it's the m of t. Now we want to know what the m of 1 is, and we want to know what the m of 2 is. So let's waste no time. Let's bring the calculator up. We're going to say it's 50 times 1 cubed minus 300 times 1. Of course, we know that'll make no difference. Plus 4,000. And we're going to get 3750. So let's write that down. 3750. Right, now we pull it up and we're going to put in 2. So we're going to go 50 times 2 cubed minus 300 times 2 plus 4,000. We get 3800. So we have a coordinate 1, 3750, and a coordinate 2, 3800. And remember, average means we are going to work out the gradient. So it's going to be 3800 minus 3750, 2 minus 1, which if I subtract there, I'm going to get 50 over 1, which is 50. So the average rate of change in publication, in circulation, was 50 magazines. Okay, so that's easy enough. Now it says, when will it have the least sale? So now we need the derivative again. So we're going back to our derivative equation, which is 150t squared minus 300. Why am I doing that? Least is the same as saying the word minimum. Remember what I said to you, as soon as you hear the word minimum or maximum, you know you must put the derivative equal to naught. So we're going to put this equal to naught, and we're going to solve out when it will be the least. So 300 equals 150t squared, which means t squared is equal to 2, which means t is plus or minus root 2, which means obviously, because t is time, can't be negative, it's going to be root 2. And so what we should do is just go and quickly look on the calculator what that would be. The root of 2 equals, and we take it to decimal, 1,4. So what we could do is we could go 1,41 years, but it would make more sense to pull that up and do some things. So we'd subtract the year. We find we get that, which in decimal form is that, and we times that by 12 to find out how many months. And again, to decimals, it looks like 5 months, so it's 1 year, 5 months. Lovely. So that brings us to the end of that question. Right, let's see how another question would look in this section. Right, this has got to do with a bit of science. It says a bullet is shot up vertically into the air. The height of the bullet, s meters above the ground, attained t seconds after being shot upwards, is given by that equation. Right, what's important here? What's important is to know we're working in meters and we're working in seconds, because that's going to become important, and we have to know the equation. Now, if we wanted to, we could have written this equation as s of t equals 200t minus 5t squared. And they may do that in the exam. This exam question I took didn't do that. It just wrote that. Now it says determine the speed of the bullet. Speed, remember, is the same as saying velocity. Now this is where this little story I gave you, where we started with s. To get to v, we took the derivative of s. So we're going to do the same thing here. We're going to say the velocity at t is equal to the derivative of that, which is 200 minus 10t. Now they want to know the velocity after 4 seconds. So the velocity at 4 is going to be 200 minus 10 times 4, which is going to be 200 minus 40, are 200 minus 40, which is 160. Now, what about the units? We are looking at the meters divided by the seconds in terms of the change in displacement over the change in time. So it's meters per second, and you might have been shown to write your units like that. Either one is absolutely fine. You can take your pick. Okay, so we found that at 4 seconds, the velocity of the bullet is 160 meters per second. Okay, so that's great. Now, what does the next question say? The next question says, calculate the maximum height. Now, you see the word maximum, you think derivative, and we want to maximize the height. So we've got to use the S equation's derivative. Okay, if I wanted to maximize the velocity, then I would use the velocity equation. So I've already got that. I know that S dashed of t is actually 200 minus 10t. And so if I want to maximize for a max, I put the derivative equal to 0. So 0 is equal to 200 minus 10t. So 10t is equal to 200, which means t is equal to 20. So at 20 seconds, the maximum height is reached on this bullet. Now it says, after how many seconds is the speed of the bullet that? Now remember I said to you about the units, you could write it like this as well. Now notice it's got a negative on it. This one I had earlier on, 140, was a positive. Now all that means is that it's changed direction. So we've shot the bullet up, it's gone up using positive velocity, and it's obviously returning with negative velocity, just showing the direction is now different. Okay, so don't get worried about that. That's not a problem. All you're going to do is you're going to say, look, I know my velocity equation was 200 minus 10t, and I want it to equal minus 100. So I want to find out when that time would happen. Right, so let's have a look what we're doing. We're saying 10t then is equal to 200 plus 100. So 10t is 300, which means t is equal to 30. So at 30 seconds, we will reach the speed of minus 100 meters per second. Okay, now it says, after how long will the bullet hit the ground? Now the ground is where S happens. Okay, so just to remind myself what that equation was, let's just go back to what S was. S is 200t minus 5t squared. 200t minus 5t squared. So if it's going to hit the ground, do you agree with me, its displacement would be 0. It would be back to where it started. And so I would have this, and all I would do now is I would solve this. So I would say to myself, right, great, let's do this. 0 is equal to, take out the 5t. I'm left with 40 minus t, and therefore t is 0 or t is 40. Obviously 0 is when it was fired, so this is when it comes back to the ground again. So at 40 seconds, it hits the ground. Lovely little question. Some insight involved, really, really nice to see. Let's glance at the next one, and if it's not too long, we can quickly squeeze it in. So let's see what it says. Okay, it says the depth measured in millimeters of water in a pot T minutes after it starts to boil is given by that equation. So let's highlight the equation. Right, now the question says, how many millimeters of water are there in their pot just as it starts to boil? Now remember I said to you the word starts, what should immediately spring to mind? T is equal to 0. So what are they asking you? How much water is there in the pot? They've given you an equation for the depth of the water, so it would be straight substitution into this equation. So let's do it. So it's D of 0 equals 86 minus 1/8 times 0 minus 1/4 times 0 cubed. And we're so delighted that these are zeros because we know the answer is going to be 86 millimeters of water. Now we go to the next question, and it says, find the rate at which the water level is decreasing. So they're actually telling you something there when T is 2. So right, let's look at it. Rate. As soon as I see the word rate, I know it's the derivative. So we know the equation was D of T is equal to 86 minus 1/8 of T minus 1/4 T cubed. So the first thing we're going to do is we're going to find the derivative. So d dashed of t is equal to, so 86's derivative falls away because it's a constant. This becomes minus an eighth, and this is going to become minus 3/4 t squared. Now, if you look at that equation, it's a negative here. Something squared will always be positive times a negative, so it's clearly negative. So this answer will always be negative, which is why they're saying decreasing. I've just picked up the equation by mistake, but don't worry, it's back where it should be. Right, so what am I doing here? At 2 minutes, I would say the derivative at 2, which is equal to minus an eighth minus 3/4 times 2 squared. Now, the good news is that's easy arithmetic, so I cannot be lazy. I'll do it mentally. It's 3/4 times 4. That will divide into that. So I've got minus 1/8 minus 3. And so it's decreasing at minus 3 1/8 millimeters per minute. Okay, because the unit was millimeters and the time was minutes. All right, so let's look at the next question then. What are they asking next? When will the level of the water be dropping at a rate of 12 1/8 millimeter per minute? Now, they've used the word dropping for a reason. They're telling you in another word, decreasing. And if it's decreasing, do you agree with me, this must be negative 12 1/8. So what we would be doing is we'd be taking the derivative and we would be putting that equal to negative 12 1/8. Right, so now it's just a matter of working with our delightful fractions. If we do that, we've got minus 12 1/8 plus 1/8 equals minus 3/4 t squared. That's going to give me minus 12 is equal to minus 3/4 t squared. And if I times by 4, I'm going to get minus 48 is minus 3t squared. Dividing by minus 316 is equal to t squared. So t is plus or minus 4. But obviously, if we're dealing with time, it can't be the negative. It must just be the positive. And so the answer is, at 4 minutes, the rate of decrease of the height of the water would be minus, well, 12 1/8. Okay, so that brings us to the end of this session. And I'm sure you can see why I got so excited about calculus. I know you're probably thinking she really has to get a life, but I promise you, you'll see as you go on, and if you do mathematics at university, how useful this particular section will be. So great being with you, and I hope you enjoy your day, and I look forward to next time. Thank you.